But how do drones fly? Apart from the electronic flight system, a drone also needs a battery, motors, and propellers, commonly called blades. The motors rotate the blades at high speed. The Parrot AR drone, for example, can rotate its blades at over 28,000 revolutions per minute, or 475 revolutions per second. The formula for calculating lift is given as 1/2 the density of air, shown as ρ, times the velocity v squared, times the surface area A of the blade, times the coefficient of lift c subscript L, which is based on the blade's surface area and an angle of attack. The only value that a drone will ultimately have control over is the velocity, as it rotates its blades. Drone movement in the 3 axes, as for aircraft, borrows from naval terminology. Rolling is from left or right as viewed toward the front of a boat. Pitching is the front moving up or down, and yawing is the boat pivoting or turning toward the left or right. The 4 motors and blades are divided into 2 sets. One set will rotate clockwise and the other will rotate counterclockwise. The first thing a drone must do is get off the ground. To do this, it must use all 4 of its motors and blades to generate a net force upward that is greater than its own weight. The red arrows represent the thrust generated by each motor and blade. Once airborne, the drone will hover. To do this, the net force upward needs to match its own weight to achieve equilibrium. The green arrows represent the thrust generated by each motor and blade to achieve this balance. To roll to our left, the drone will increase the power to the motors on the right, which increases the thrust, shown by red arrows, and decreases the power to the motors on the left. The reduced thrust is shown by blue arrows. The resulting net force will roll the drone to our left. Notice I mentioned our left, as the drone is facing towards us. It would be called rolling to its right. This situation is called control reversal by drone operators, and can be a source of confusion and mishaps during flight. To roll back to our right, the drone will reverse the process. To pitch forward, the drone will increase power to the 2 back motors and reduce power to the 2 front motors. The resulting net force will pitch the nose of the drone down and it will move towards us. To pitch backwards away from us, the drone will reverse the process. To yaw in a clockwise direction as viewed from above, the drone will increase power to the front left and back right motors, which are rotating counterclockwise, and also decrease the power to the front right and back left motors, which are rotating clockwise. An increase in thrust is shown with red arrows, and a decrease in thrust is shown with blue arrows. The net thrust upward will remain roughly the same. However, the drone is now generating more counterclockwise angular momentum, so to conserve angular momentum, the drone will begin to yaw clockwise. Now for flying with a real drone. As you will see, hovering requires constant adjustments by the onboard flight system, especially when a mild breeze from the right tries to push the drone, and it reacts. I instruct the drone to roll to our left. Remember the control reversal I mentioned earlier? So this is actually a roll to the drone's right. Now I instruct the drone to pitch forward towards the camera and then to pitch backwards away from it. As I instruct the drone to yaw clockwise, you will see that the breeze will try to nudge it slightly to the left. The technology used in drones is constantly changing, so will its future uses, and the sky really is